So today we're going to use Maple to explore some situations that can be modeled using exponential functions. The first situation we're going to look at is the following. So between 9 and 10 p.m., cars arrive at a fast food drive-thru at the rate of 12 cars per hour, which is 0.2 cars per minute. The probability that a car will arrive within t minutes of 9 p.m. is determined by the formula f of t is equal to 1 minus e to the minus 0.2t, where e is the Euler coefficient. First of all, let's define our function. We want f to take t to 1 minus e to the minus 0.2t. Now, powers of e in Maple have a special predefined command, which is exp. So if we want e to the minus 0.2t, we would type exp of minus 0.2t. There's our exponential function defined in Maple. So what can we do with this? First, well, ask it, what is the probability that a car will arrive within a certain number of minutes of 9 p.m.? So let's start with 5. What is the probability that a car will arrive within 5 minutes of 9 p.m.? Of course, to evaluate that, that's just asking what is f when t is 5. So we evaluate f of 5. And that's what we get. Again, we've done this before. If we want to round that off a tad, we give it what we want to evaluate. We're going to use percent to indicate the most recent evaluated expression and tell it how many digits we want. Let's ask for 4. So we see that the probability that a car will arrive within 5 minutes of 9 p.m. is about 0.6321. And I've written my answer there in text mode. So let's look at a couple more probabilities. What is the probability that a car will arrive within 30 minutes of 9 p.m.? So that is, of course, asking for our function f, but evaluated at 30. And there's our answer there. And of course, you could round that to 4 digits using this same command, evalf %4. And again, putting the answer in text mode, we see that the probability that a car will arrive within 30 minutes of 9 p.m. is about 0.9975. So let's ask for one more. What is the probability that a car will arrive within 45 minutes of 9 p.m.? So that, of course, is asking us to evaluate our function f at t equals 45 minutes. And there's the answer we get. And actually, if we round this off to 4 digits, we're just going to end up with 1. But what I want you to see from looking at this progression as t gets higher and higher and higher is that as t gets larger, our function is approaching a horizontal asymptote of y equals 1. And this becomes really obvious when we look at the graph. So we're going to plot f of t, but we're also going to plot the function y equals 1. And we're going to take t equaling 0 to 60 minutes. And we get something that looks like this. So we see that the function is very quickly approaching its asymptote of f of t is equal to 1, but it's not actually crossing it. So now let's look at a second example. Clear all my definitions. All right, so alcohol and driving. It says, recent medical research suggests that the relative risk of having an accident while driving a car can be modeled by the equation R equals e to the kx, where x is the concentration of alcohol in the blood, and k is constant. So one thing we might want to do is to find the constant if the relative risk of a person having an accident who has a blood alcohol content of 0.02% is 1.4, which would mean that if a person has that blood alcohol content, they're 1.4 times more likely to have an accident than someone who doesn't have any alcohol in their system. All right, that should say find. So how do we do this? Our eventual function is going to be a function with an x, which will stand for blood alcohol content. But if we're actually trying to solve for the constant k, we would instead define, using the information we've just been given, a function that takes the constant k to e to the, now we've been given here that x is 0.02, so we're just going to use that times k. And then we're just going to solve that. Well, what is the R that goes with a blood alcohol content of 0.02%? That R is equal to 1.4. So we're going to solve for this R of k being equal to 1.4. And that is what we get. Let's round that off a tad. So that means that given this one data point and the fact that we know we've got an exponential function modeling this situation, the actual function modeling the situation now is R equals e to the 16.82x, where x is the blood alcohol content. So let's go ahead and define that function now. We're going to now define R colon equals x, and x is going to stand for blood alcohol content, and that's going to go to e to the 16.82x. Notice that this definition now overrides the previous definition of R. So we can no longer use the definition of R that we defined up here with k, because the x definition has now overridden it. So now you can, of course, use this to answer questions. We can ask for the relative risk if the blood alcohol content is 0.17%. Of course, that's just asking what is R of 0.17. And I'm just going to go ahead and round this one off by hand. So the relative risk is about 17.5, which would mean that a person with blood alcohol content of 0.17 is 17.5 times more likely to have an accident than someone with 0 blood alcohol content. We can also, of course, answer questions like the following. What blood alcohol content would correspond to a relative risk of 100? So at what blood alcohol content would a person be 100 times more likely to get in an accident? And of course, this is asking for the x value that would have an R of x value of 100. So that's done using the solve command, and we're solving for x. We're solving R of x is equal to 100. Now let's round that off a tad. Maybe we'll round it to 2 because we only had 4 digits in our k, so that's already been rounded. So we can't guarantee that our answer is accurate to 4 decimal places, so let's use 2. And we see that for a blood alcohol concentration of 0.27%, the relative risk of an accident is 100. So those are 2 of the sort of problems that are modeled using exponential functions and a few ways of working with exponential functions using Maple 17.